So hi guys, uh, the problem we're going to solve today is fruits into baskets 3. Let's quickly read the problem statement. You are given two arrays of integers fruits and baskets, each of length n, where fruits of I represents the quantity of the ith type of the fruit and baskets of j represents the capacity of the jth basket. So they've given us two independent arrays. Uh, these are these represents the fruits that we have and the quantity of each of the fruits. So ith index has the quantity of the ith type of fruit. So that's what this array is about. And this is, you have length of baskets, number of baskets, and each index refers to the size of the ith basket. So now, from left to right, place the fruits according to these rules. Each fruit type must be placed in the leftmost available basket with a capacity greater than or equal to the quantity of that fruit type. And each basket can only have one type of fruit. If a fruit type cannot be placed in any basket, it remains unplaced. So the rules for placing the fruits in the baskets is that first of all, you have to scan from the left to the right, uh, and you have to place in the first available basket. So if a fruit has 4 as its quantity, has 4 number of you know there are 4, uh, the fruit number 0, the quantity of fruit number 0, like at index 0 is 4, then you need a basket that is at least 4 in capacity. So 4 or more in capacity. uh, Anything less than that, you cannot place that fruit. And the other rule is that you can only place one particular fruit type in a given basket. And you can place a particular fruit type in only one basket. You cannot divide and place it. Either you place all the fruits of a particular type in a single basket, or don't place it at all. uh, that is the constraint that we have. And we need to find, after following all of these rules, we need to find the number of fruit types that we couldn't place. So that's what the question is about. Let's do a dry run and figure out, let's try to understand the question a little bit deeper. So you can see here, let's copy the question. Fruits equal to 4 to 5, baskets equals 3 5 4. So let's start by placing the by placing the uh, zeroth fruit type. Uh, the quantity of the zeroth fruit type is 4. There are 4 number of fruits of type 0. So now we have to place this in a bag of capacity at least 4. So let's just try to find such a bag. This you cannot. This is a smaller bag. You need to find a little bigger bag. And here this is the first bag that is, that you can use to successfully place the fruit of type 0. So this will go in this bag. Now this bag is used. Secondly, you have the second, the type 1 fruit. Uh, so the fruit of type 1, the quantity of that is 2. So you have 2 fruits of type 1. Now, this you can place here, right? This itself is big enough for placing this fruit. Now, finally, you have 5, basically type 2, you have 5 fruits. Now, this you cannot place anywhere, right? So, because of that, this fruit is not, this fruit you cannot place it. So, this is a fruit that you cannot place because the quantity of that fruit type is 5, and we don't have a bag which is not used right now, and which is big enough to keep that particular fruit type. So the answer here would be unplaced count equal to 1. So, and this is exactly what we have to return now. So that would be that should clear up the question. But the interesting part that you should note here would be the constraint of the problem. Uh, so if you go down here, right, the length of the fruits array and the baskets array is going to be the same, and it's going to be equal to n, and n can range from 1 to 10 to the power 5. Now, if you're going to adopt this approach, where you took each fruit type and try to place in an available basket by scanning from left to right, it will take you O of n square time, which is not something that is feasible with 10 to the power 5 constraint. So we need a smarter way to do this. So let's try this one more time. 425 354. Now you take this particular fruit. The answer to the question, like the question for which you need the answer to, is the first index or the first basket from the left in which you can place this particular fruit, uh, which will be the basket, or the basket which is just bigger, or just like equal to or just bigger than this particular this quantity 4. Now uh, since it's 10 to the power 5, one obvious thing you can try is to do a binary search. But since this is not a sorted array, it's not possible to do a binary search also here. So we have to apply a trickier concept here called segment tree. So I'll quickly brief over segment tree for those who don't know about it. Uh, and once I explain, once we understand what segment tree is, it will become clearer why segment tree is a better approach here. So segment tree is a simple tree. You can see here. So this is what a segment tree is. So we have the basket array of 3, 5, 4. Now you can build a segment tree out of this array. Segment tree can have any function. Now the function I'm using here is max. So segment tree is used for range queries. Right? Forget the current question. Let's take a sub question. You given an array, this particular array, you given an array ARR. You need to find, and then you have a set of queries that are coming, range queries. You need to find the maximum in these ranges. How would you do it? You can again, for each query you can iterate through that particular interval and then find out the maximum for it, but again that will cost you O of n square time. How can you find the maximum of a particular range uh, in logarithmic time? That's where segment tree comes in. So if you look at this, right, you have so this is the entire range 0 to 2. All I'm doing here is similar to binary search. I'm just splitting this entire range into two equal subranges. So 0 to 1 and 2 to 2. Now 0 to 1 again can be split to 0, 0 and 1, 1. So left half and the right half. So I'm just splitting it in the middle and then distributing it into two halves. So basically you have left and you have right here. So mid will be equal to left plus right by 2. And this will be left to mid, and this will be mid plus 1 to right. And each node will hold the value of the function that we're using to construct the segment tree. Here we're using the max function. So you can see here, this node will hold the value of max of elements of ARR from 0 to 2, which is 5. Now this gets recursively constructed based on the children. You keep splitting based on your range, and once you reach the leaf node, right here, the answer will be the array element itself. So here you can see 3 is the array. So you can see the max of this element is the same 3 itself. Max of this element is 5 itself, first element. And when you have to, then you can use these two, the computation of these two, sub nodes to calculate the value of the parent node. So 3 and 5 max will be 5. So that will give you the maximum for the range 0 to 1. And similarly, you can calculate the maximum for 0 to 2 by taking the max of these, and that is 5. So that's how you recursively construct a segment tree. Now, so once you have a segment tree, you can find the maximum of any range. For example, you would like to find the maximum of 1 to 2. That's the most difficult one. All the other ranges are covered, I guess. Have to find 1 to 2. How do you do it? you go down this path 0 to 2. Now it has more than what you need, right? So uh, you go to the left or you go to the right. Now you can see you have your there are parts in the left as well as in the right. So you go to the left first, because 0 to 1 is definitely part of 1 to 2. And here you can again, you can see 0 to 1, there is 0 part which is not there in the range. So you have to go to the right, because this is already there in the left. So you go to the right. Now 1 to 1 is completely part of the range, so you take this 5, you return, you go back, traverse back. And now again, you haven't completed the range, it's just 1 you have completed. So now you need to go to the right. You can see 2 to 2 is completely part of the range. So this and 4, the maximum will be 5, and 1 to 2, the maximum is 5. So you can find, and this will take log of n time for the query. For building the segment tree, it will easily take O of n time for building, and the query will take logarithmic of n time. Yeah. So that's how you find the range max using using a segment tree. Now assume Q is also of order n, or order 10 to the power 5, and array is also of order 10 to the power 5. Using this approach, you can find the range, the maximum for each of the each of the ranges in O of n log n time, as opposed to O of n time if you're adopting the brute force approach. Sorry, O of n square time if you're adopting the brute force approach. So that's how segment tree helps us here. Now another concept that you should have in segment tree is how would you now if you add another twist to the question, you would like to update an index in the parent array. How would you do that? While as in when you take the find answer these queries, some of these queries, instead of asking for the max, will ask you to update an index in the parent array, and then you have to proceed with the subsequent arrays. So that can be an alternative question. So that is where point update comes. Basically, you update a particular index, a particular point in the main array, and then you have to rebuild the array so that this update is propagated to all the segment tree nodes. How would you do that? So that'll be really simple, as simple as building the entire array. Actually, much simpler than that. Suppose first you have to get to that particular node. You can just traverse, do a binary search in order to get to the particular node. Suppose you are changing this particular node to 2. Once you've done that, you just have to recurse back and then take the max of these two. Again, this will get updated to 3, and again you have to take max of these two. This will get updated to 3. So, and even the point update, right? This will also take O of log n time. So that's how efficient this segment tree is, and yeah, it basically helps you do range queries in a logarithmic time. To summarize what segment tree is, it the topic does sound strange, but it is really straightforward here. Now, uh, so now that we have an understanding of segment trees, let's dive back to the original problem that we had. So if we construct a segment tree for this particular the original array was 354, the basket array. Now this is 0 to 2, this is 0 to 1, 0, 1, and this will be uh, 2, right? So all we have to do here, for each of the, once we build the segment tree, all we have to do here is for each of the fruits, 4 to 5, right? For each of the fruits, you have to go down the segment tree, do a binary search or something similar to a binary search, and find the node in the original array. So a node in the original array will correspond to a leaf node in segment tree of that particular array. So you need to find a leaf node which is uh, greater than or equal to basket of I. So this is what you have to do. And once you have done that, you have to do a point update on that particular index. Now you'll do the point update and make that particular basket capacity as -1 so that it cannot be used by any other fruits anymore. I think you can even do it as 0, but I'm just going with -1 over here. Uh, so just checking if you can do with 0. Yeah, since the fruits of I, the minimum size is 1. If you want to just completely disregard a basket or mark it as used, you can just mark it as 0 or -1 or anything that is less than 1, so that it cannot be used by any subsequent fruits anymore. So if you do these two, you'll get the answer. You'll get the answer to the question, to the original question. Uh, Basically, if you keep doing it, you might get the final answer as -1, because there's no basket to place that particular fruit in. Basically, there is no basket whose size is greater than or equal to the quantity of the fruit type. So in that case, you can keep track of number of such fruits you get out of segment tree searches, and ultimately return that output. So that's all that you have to do in this question. Let's do a dry run over here. So you go with 4, right? Now, so I'm going to use this to mark it as unplaced. And I'll use this to mark it as placed. So I'm going to go with this guy, 4. So I'll do a binary search to find this particular basket, and I'll start from the left side first. So binary search I'll do in left to right, so that I'll find the lowest index first, because we have to traverse the array from left to right. So I'll take the left node first and then go to the right node, so that that order constraint that you have to go from the left to the right in the parent array is maintained. So let's try placing 4 over here. You have 5, that means you can actually place something. Now you try to go to the left side, it's still 5, you can place it, you don't have to go to the right side now. Okay, now 3 is actually less than 4, so you cannot go here. You cannot go here. Instead, you go here. So here it's 5, and you've reached a leaf node over here. So since you've reached a leaf node, all you have to do here is make this -1. Once you've made this -1, what will happen is, while you traverse back, you just need to update the parents. So this max becomes 3, and this max becomes 4. There you go. You placed successfully. You also return a status update to the parent, so that you can finally keep track of number of unplaced or placed fruits. So here you'll return a true, true, and finally this becomes true. Now let's do the same thing for now let's do the same thing for the next element, that is 2. So again, 2, you go to the left. So if it's 4, that means you do have some bucket, some basket, which will satisfy, which you can use to place this particular fruit. So you're happy, you go to the left. You find 3 here, which means you can place in the yeah, which means you can place in you can go to the left. Now when which means like here, like you reach 3 is definitely greater than or equal to 2, So again, you're still happy that you have a basket below it. You start by going to the left first because you need to maintain the left to right order. Now when you go to the left, you encounter 3, which is a leaf node and which satisfies its condition. So you're all happy. You just make this also -1, -1, -1, the max. You return true on the way back. This also becomes -1, and over here it still is 4, and then you return true. So this also becomes placed. Now you're left with 5. Now you count with 5, but you realize here that 4 is less than equal to 5. It's less than 5. It's not greater than equal to 5, which means you don't have a basket below it. You don't really have a basket in the main array, which you can use to place that particular fruit. So immediately you don't have to go down anymore. You can just return from here itself as false. You can immediately return from here itself as false, and there you go. So you have one unplaced element, so you can return the answer as 1 over here, and that's pretty much it about the question. Uh, Before I go into the implementation of this problem, I'd like to add a couple more things about how you implement a segment tree. So the segment tree, you will be keeping it in an array called seg. The size of the seg array will at max go to 4 times the length of the original array. Now this is a proven thing. There are there are proofs for this, but you can just assume that always when you're building a segment tree, uh, the length of the segment tree array is at max gonna be 4 times the length of the uh, original array at max. So and the way you store a tree in an array, with the way you serialize a tree into an array, is as simple as is the same as the way you do it for a normal binary tree. So ith index node will reside at, sorry, the children of ith index will reside at 2 into I plus 1 and 2 into I plus 2 for the left and the right children respectively. The left child of ith index, in the segment tree array, will reside at 2i plus 1th index, and the right child of the ith index or ith index in the segment tree array will reside at 2i plus 1, 2i plus 2th index in the segment tree array. So that's how it's going to be. And yeah, that's pretty much it. So yeah, let's dive into the implementation. I think I'll walk over the implementation as well, so that you can understand how you can build the segment tree and how you can run queries on it after that. Okay. So I have a segment tree class. I've defined a segment tree class which includes all the segment tree stuff, and I'm just uh, outside the segment tree. Once you can assume the segment tree is built for now. Uh, Once that is built, all you have to do is use the segment tree, the search feature. Once you've built the segment tree over here by passing the basket array into the segment tree, all you have to do is just keep searching for uh, a basket for each of the fruit types, and in case you get false, you just update the unplaced variable and then return the unplaced variable at the end after processing all the fruit types. So that's all that is there in the main code. Let's now deep dive into the segment tree code, which has the actual meat of the problem. So as I discussed, you have a segment tree array which I initialized to the 4 times the size of the original array. Now you have two functions, which is build tree, which is used to build the segment tree from the original array, and I also have a search function which will do binary search and find you the index of the basket that matches all the constraints for that particular fruit type, and we'll also do a point update and propagate the point update throughout the segment tree. So all of that will reside in this particular function. So let's first start by analyzing the build tree function. Now this is, both of these are going to use recursion, which is something you commonly use for tree traversals. So the first parameter is going to be the index in the segment tree. This is required for the recursion, and you have the original array that you're going to pass in order to build the segment tree. Then you have the left and right, which is the range. So these three, I, left, and right, you're going to continuously use for recursion. Now, the first breaking case is that if left equal to right, then it becomes then you can say the ith node is a leaf node. So that is why we need the left and right. That is one of the reasons why we need left and right. So this will tell you that you reached a leaf node, and if you've reached a leaf node, then the value of the ith index in the segment tree is going to be the value of that particular basket. Basically, left there's only going to be one index in that particular range because left equal to right. So it's going to be equal to the value in the original array for that particular basket. It's just going to be the value in the original array. So you just update the segment tree with that particular point value, and you return. So this is the base case. Now, in all other cases, you have to divide your full range into two halves, the left and the right half. Again, you find the mid, you pass, you do recursively call the build array, you put the left child at 2i plus 1 index and the right child at 2i plus 2 index, and you pass the corresponding ranges. And once you've done that, you update the current index of the segment tree with the max value of the children. So this is where you use the segment tree function, and that's pretty much for the build tree function. Now moving on to the search function. So here also, since we have to use recursion, we have the I, left and right, and instead of the array, here we are passing the element to search. Here what we're going to check is the leftmost basket, which is available and which is greater than or equal to, which has a capacity that is greater than or equal to x. That is what we're going to check here. First of all, if the parent array, parent node itself, the value of the parent node itself is less than x, then there's no hope of finding a particular basket under it. That's something we discussed already. So we return false immediately. We don't have to travel. We don't have to go to the children at all. The second base condition is if you reach the leaf node, then you found the basket. In which case you have to do a point update. You update it as -1 and then return true since you found a basket. Now, in neither of these cases, we have to do our recursion. So you find the mid, left plus right by 2, and then you search the left child first. You check if you have found a value in the left child, in which case the result will be true. You found a basket. If you found the basket in the left subtree, then the result will be true. If not, go and do the same thing in the right subtree. And at the end, you have to, since you've done the point update, you have to do the updation of the current index just like you did in the build tree function. Just copy that down here. Exactly ditto. You just go to the children and then ask for their value and compute and apply the function again, because they might have gotten updated. Might have is key, because it may not have even gotten updated. And then you return the result, which is basically if you found a basket or not. Then again, so that's all that is there about the search function. You've done the build, you search a basket for each of the fruits, and then you keep track of the fruit types for which you couldn't find any basket based on the result that is returned by the search function, and then finally you return the unplaced value. That's all that is there for this particular question. Let's try running it, and bingo, there you go.